Hello, everyone, and welcome to today's webinar, Specifying UHP Valves for ALD Processes. My name is John Butler. I'm the Communications Manager for Semiconductor at Swagelok Corporate, and I'll be your moderator today. In semiconductor chip fabrication, fluid system components and assemblies play a crucial role and must meet exacting performance criteria. In addition to meeting the challenges presented by extreme precision, we also need to consider UHP cleanliness, leak tightness at high pressures, high process temperatures, and the hazardous nature of many of the precursor gases used in ALD processes. During this webinar today, we'll examine the challenges semiconductor fabricators encounter and how the right ALD process valves, as well as other fluid system components, can help address and overcome these challenges. Our presenter today is Mr. Malik, who is the Regional Marketing Manager for the Americas and EMEA for Semiconductor here at Swagelok. Just a little background on Masur. In his role as Regional Marketing Manager, he is responsible for identifying, assessing, and developing marketing programs to address Swagelok's organizational needs in this critical business segment. He has been with Swagelok for 22 years, and in previous roles, he has served in various capacities, including project management and supervision of quality, engineering, and material science programs. Just some general housekeeping before we get rolling. Following the presentation, we will have a short question and answer session. You can add your questions at any time to the Q&A tab at the top of your screen, and we will take as many of those questions as we can at the end. So with that, I will turn it over to Masur.
Wonderful. Thank you so much, John. I really appreciate for that great introduction. Really looking forward to this presentation. It's an exciting time in semi these days. We're all extremely busy and we're enjoying the ramp in the semi. And what a great time to talk about, the things that are going to improve our processes and profitability and everything else. So I just wanted to start with, just setting the stage for what we're going to be doing today. And then, we'll go into the details of the presentation and then stop for Q&A at the end. So, if you really look at it, it's extremely important to partner with our customers in the semiconductor market. And this is evident by our deep understanding and of the dynamics that drive the business of anybody's customer. So anybody's customer, we should be able to understand their business, and we need to be singularly focused on addressing those challenges. The knowledge, no other industry move as fast as semi or requires the technological experience and proficiency of semiconductor market. If you look at the productivity side of things, every square millimeter of tool in the facilities that needs to deliver the precision and the speed and the cleanliness all day, every day. So it's not hey, let's do it in the morning and in the evening we can take a break. This is all in. We are always on. System health, maximize the uptime, minimize the maintenance time and the expenses that goes along with it. And last but not least, the most important is the exclusive focus on the safety of every process, every application, and which is the foundation of every activity that happens in a fab environment. If you look at today's presentation, what we're going to talk about is we really want to have the discussion around some of these common challenges that we see and some of the ways that we overcome them. And at the end of this presentation, you should be able to understand the typical advanced wafer process challenges. How do we manage some of those issues? We recognize some of the specific ALD process challenges. I know a lot of people are here to listen to the ALD processes challenges. And then we'll end the presentation with appreciating just the innovation in today's valve technology and how important it is becoming to stay ahead of the market. And all of those things are basically combined into handling the unstable chemistries, maximizing the production yields, and reducing the total cost of ownership. So we will try using these three uh, ideas about the handling the chemistries and production yields and total cost of ownership, and we'll try to change those challenges into the opportunities. And like John said, please add your questions in the chat and we'll continue to monitor it, and then we'll try to answer them towards the end of the presentation. So, the processes are getting more and more complex. Chemistries are getting complex, requiring higher temperatures, higher pressures. The chemistries that, the material of use has to be corrosion resistant at a higher degree, and you name it. There's so many things that are coming up with these chemistries as we are moving forward in our industry. And also the race to make a smaller and smaller width of logic chips, or adding the layers and layers on 3D for the memory chip. These are all coming up through those challenging chemistries that are being introduced. And one of our challenges is that how do you bring the most chemical process into the process in the shortest amount of time? So we're going to be talking about unstable chemistries and how can we look at that as an opportunity and make some recommendations there. The other big aspect that we are looking at is the process conformity and yield. And it's all about productivity. So process conformity and yield is all about productivity. Talking to Intels and Samsungs of the world, the fab owners, it's about the yield we can get out of each wafer and how fast can we get each wafer processed. We have grown in sizes from 150 millimeter wafers to 200 millimeter wafers to 300 millimeter wafers, and we even dabbled at one time at 450 millimeter wafers. And if there are any defects on these wafers, so as an example on this slide, if you look at these red dots that are identified in an inspection, if you see any defects in these wafers, that's loss of productivity. That's loss of profitability for anybody that is running that fab. And you can imagine how important it becomes when you're trying to use products and making sure that each wafer does not have any defects. So loss of process yield means loss of productivity. So very important for our industry that process conformity and yields stay extremely, extremely high. So we're going to talk about that a little bit. And then the third and the most important aspect that we are looking at today is going to be the total cost of ownership. When we're looking at our processes and systems, sometimes it becomes as trivial as a valve and a fitting or a component, and we start looking at these minute things. How can we save money here? What can we do to do this, and what can we do to do that? And we're not looking at the overall system, but it's extremely important. A valve may cost like $100 or $500, $1,000. But if you look in the bigger scheme of things, if a tool or if it's a process or a system that's shut down in a fab, it's going to take, you know, delays and shutdowns. All those things are going to cost enormous amount of money compared to what that valve or fitting or something that we were considering. So we always have to look at both the visible cost and the invisible cost and try to minimize the delays and shutdowns. So you'll see some of the things that we're going to talk about, how to look at the cost of ownerships also. So the three factors that we're talking about today is the unstable chemistries, the process conformity and yield, and the cost of ownership. And we look at, when we're looking at the end customer of these products, like fab owners, like I mentioned, Intel and Samsung, they're spending billions of dollars with a B, billions of dollars to build these fabs. And they want extreme uptime for these tools and these processes. They would like to maximize the return on investment, and they want to recuperate the cost as soon as possible So they're never happy with the stoppage or delay or processing non-conformity and things like that. So there are several factors that you'll hear about today, but these are the ones that I just wanted to highlight. There's several other factors that we can look at, but they're the ones that I picked that we hear most about from our customers or our colleagues. So these are the items that I'm going to highlight. Like I said, unstable chemistries, the process yields, conformity, and the total cost of ownership, one by one. And how do we translate all of this into productivity? Let's look at the first one, managing unstable chemistries. When we talk about managing unstable chemistries, we're always looking at the right kind of valves, right kind of material, the pressures, the temperatures, and so on and so forth. We always have to have that fundamental basics that we have to take care of. And we all work in the design field. Most of us on the call, I was looking at the list of attendees. We all work in the design field and we understand it really well, that all of those things are pretty critical. But one of the things that I wanted to highlight today, which is sometime overlooked, is the improving the purgeability of the system. And it is sometimes not considered as critical, but it is one of the important factors that has to be in a design. If you have a valve in the system, it's critical to ensure the chemistries are purged as fast as it can, so the next set of chemistries can enter the chamber for the next reaction. This is especially critical for ALD process. If you have a one valve, where it's being used and how it's being used, it becomes even more important. So we'll give you a couple examples in following slides as we move forward. The other one is the valve selection, the picking the right valve for the application. So like I mentioned earlier, we need to look at the pressures, the temperatures, the materials, but also, again, I keep highlighting is the purgeability of the valve. What are we using in the system? The chemical compatibility, the timing, the response times, the flow rates. So there's so many factors that you have to consider in managing the chemistries, that you have to have the right valve to start the design process. If you look at a single valve, when we look at a single valve in improving the purgeability, it doesn't have the purging capability on its own. Obviously, it has to, have a circuit introduced into it to be able to, purge it, or it will be cumbersome to purge it and be able to use it. But when you add another valve in the loop or another circuit or a flow circuit in the loop, we have just added a quick purging ability. By adding another valve or circuit, now you have the capability to be having that purge capability built into the system. And you can do it two different ways. One is multi-valve manifolds. When we look at the multi-valve manifolds, we have added a purge port into it, and we can use the purge port and the process port, which is on the left-hand side of this picture. If you look at the right-hand side, the other factor is the multi-port valve. So a body that has multiple ports, that one of them can be used for purging. So again, the goal is to have process with one gas, purge it quickly as possible, and introduce the next gas, purge it quickly, and so on and so forth. So when I mention this, we want to get the process gas, once it's done with the reaction, out of the chamber as quickly as possible so process can continue to the next step. As I mentioned earlier, we can do better purging with manifold valves. So let's look at this example, and this is what I wanted to highlight. We have a gas source here. If we look at the circuit right here, And it goes to a process tool on the right-hand side. So going into a gas source to a process tool. And now we have added a purge line into it. So and added a purgeability or a valve that we can use for purging the system as quickly as possible. And it goes through the mass flow controller on the left-hand side and right here. And then the purging out into another circuit that we have included into the. So now we can set up the purge out across the mass flow controller and walk through it. So good, very nicely done. The biggest drawback in this kind of circuit is that we're using about two T's right here, one T right here, and one T right here. We're using two T's and we're using 10 different wells. So you can look at how many wells that we're putting into this system. So going from the gas source, weld. So you're adding 10 wells into the system. So, obviously it creates a cumbersome system for purging. But if you look at the manifold valve for battery purging, now you take the same circuit and change it to using the manifold valve. So now we can eliminate the T's. So we have no T's. Now we have no valves. So now if you look at the valve that I showed you, the manifold valve that I showed you earlier, you have a gas source that come in, go into one of the valves, and then it's processed through the mass flow controller into the process tool. And if you look at the manifold, it's already have that built-in second valve. So now we can use this other line to be able to purge. When we close this valve, we're able to purge this in place and purge out, through this other line right here. So again, looking at these two, overall better purging without putting a single valve or single weld or T in place. This is all done without any valves or T's in place. So two valve manifold can tremendously improve the purging as well as the system design for us. And then if we compare the top, the one that we were showing earlier, to the bottom that we were showing later, there's a 6% volume reduction of the media. So obviously there is, reduction of media that's going through the system. So you look at the bottom one, we see that conversion right there. Lesser gas in the system, faster our ability to purge it out. So we're showing a significant decrease in dead volume also. So 63% reduction in the dead volume. Again, the dead volume is the volume that it's hard to get to or hard to get out when we're trying to purge without having a purge valve or purge circuit in there. So just all in all, purging is extremely important when we have complex gases, and we have to take care of that very quickly in the system. I'll leave it you with one side note. This also, we can use your own chemistry. You can use your own geometries, however you like to create the circuits. So you can have a flow circuit, you can have a purge circuit, you can have valve manifolds, you can create your own paths and other factors, anything that you want to consider for your systems. So there's a lot of ways to design your systems to ensure that you have a good purging in the system, but also allowing it to have the right flow, right temperature, right pressure, all of those things. And that can be done through the engineering to order valves. Okay. So how do we improve the process conformity and yield? So we talked about the chemistries now. Purging was the main thing, engineering to order, some of those things we can definitely look at. How would we improve the process conformity and yield? And remember, this is the, if the wafer is not processed fully, you're losing money. That's it. That's the bottom line. If the wafer is not processed fully, you're losing money. So how do we improve the conformity and yield? And what I wanted to focus on is also the ALD challenges. So we'll try to combine those ALD challenges and also the conformity, because they are intertwined, as you will see in the presentation. We are going to be improving those conformity and yields, and we'll mention how critical performance characteristics for ALD take part into that too. High cycle life, the temperature rating and control, the pulse delivery, the dosing, the precision, the repeatability of actuation, and fast and clean switching. All of these factors really become important as we examine our conformity and yield. And you'll see that they're intertwined both for ALD and for any other process for that matter. So if you look at it, the first factor that our valves have to perform at a very high cycle. When we're talking about atomic layer deposition or atomic layer etching for that matter, it has to open and close millions of times to be a viable solution for ALD process. So the valve design has to be optimized in design phase with computer-aided engineering as well as modeling. And when we develop to be the rigorously tested valve, we have to use extreme parameters to make sure it's going to perform every single time. And you should be able to request, the technical data, from your supplier on these things. But this is extremely important that we have a high cycle life valve that we're using in the ALD processes. And how do we achieve it? So the most of the ALD valves are designed below the fatigue limit on SN curve, the stress versus the number of cycle curves. And this allows the valves to perform to an ultra high cycle life. And that is what we're looking for in those millions and millions of cycles. We're looking for those as primary features, that it has to work every single time, regardless of the number of cycles that it has seen. One of the other factors that we've been talking about in the ALD and the conformity and yield is the high temperature. People are designing, like I talked about earlier, like people are designing to high temperatures so they can have better flow, better evaporation, better consistency, so they can run the processes at high temperature. So not only specifying the valves which goes to higher temperature, but also finding the valves which are consistent at high temperatures, and what are some of the things that we can do to help with that. So at high temperature, it's not only critical, but even harder to control the temperature, because now you have places where temperatures are high, there might be places where temperatures are low, and you can have issues like condensation or lack of flow or inconsistent flow. So if you look at this chart that we have created for a standard valve and a valve with a thermal isolator, the purple is the cooler temperature, and then the white is the hottest temperature on this graph. So if you look at this example, on the right-hand side is a typical actuator on a valve, and it's acting like a heat sink. So a lot of heat is coming from the body and going into the actuator and going into the environment, whichever it might be. If you look at the left-hand valve here, you look at the valve has a thermal isolator. We call it a thermal isolator right here. So these thermal isolators allow the heat to be contained and controlled in the body. And it can be better controlled and not be drawn too much into the actuator for this kind of setup. And either one is fine. One is not better than other or vice versa. It all depends on the application. So as a design person, as a design team, we have to be able to look at what our requirements are and able to control those things. And then the third thing is the controlling the temperatures by having fully immersible valves, which can withstand the whole valve can withstand the high temperature on this. So this kind of thermal stability results in high quality, consistent deposition from like 10 degrees to 200 degrees for the ALD 20 valve that is shown on the right-hand side. And it allows for utilizing of chemistries that previously may have been too difficult or expensive to use effectively. So this is a typical ALD valve where we showed you the heating paths and everything that's more isolated in the body, and with the thermal isolator, we're able to control it. But with fully immersible valves, we're able to have the valve fully immersed into the chamber or into wherever your process is, and be able to provide that effectively. Good. The next thing that we're going to talk about is the consistency of flow at high temperatures. So we're talking about high temperatures. So I thought just including something in there as we look at, again, looking at this, trying to figure this out as as the temperature goes, this is subjected to high temperature. You start seeing the ideal condition where the valves or they start losing some of their flow characteristics. Our goal is to next generation of the valves is that we have this control over the range of temperature. So when you look at the whole range of temperature the valve is being used, this will allow the tool to deliver increased throughput at those higher operating temperatures consistently each time. And then also the pulse delivery is critical. So, we talked about the high temperature over time, over the flow characteristics, but also looking at the pulse delivery and process yields and ALD processes specifically. If we can control the amount of media going through the processes every cycle, we can have better yields and we can have better performance in there. So a typical diaphragm valve on the left-hand side has a consistency of about 10%. And if you look at the right-hand side, a valve that is a typical ALD valve is about plus minus 3% CV consistency. And the next generation of valves that we're working on would have even better CV percent, the variation in there. So it's a continuous innovation process to improve the consistency of flow. The other aspect that we're looking at is the number one challenge for our OEM customer is desire for great flow consistency. So looking in the past, customer would expect plus minus 10% flow consistency that we showed. We talked about plus minus 3 flow consistency. Today the chamber matching as well as the desired consistency from dose to dose, our customers are expected that it would become even tighter and tighter. So the next generation of valves we are working on are going to allow you to have that faster response time and less variation from open to close. And this will allow the ALD processes to even get more precise. And like today it's pretty precise, but again, as the market condition, as the market demand is continue to require higher and higher performance, catching up to those and then meeting those demands is always on top of our mind. So in the ALD world, we are looking at the next generations of the valves and how it can help our customers. And I just, through a small chart very quickly, just the response time and how fast the valve can open when the command is received to by the time, it actually opened. And so we look at a lot of these things, actuation response time, when the command is given to the solenoid, and the solenoid actually react, and all those things. So we're continuously looking at that valve response time and how we can, continue to reduce that also. So the two aspect is, fast actuation and then the fast response time. Those are the two things that combine to make it a fast acting valve. So if you look at overall, so we have discussed the ALD process challenges, in light of how to improve yields and conformity, and how to, manage the unstable chemistry and all those things. And we, we're looking at the high cycle life, we're looking at the temperature rating and how do we control that. More importantly, how do we control the dose, the pulse delivery, the repeatable actuation, all those things, and how are, these impacting our processes. So when we discuss all these things, how does it all come together? What does it mean? Why is it even important for us to even discuss these things? And it's, so if we look at the three things we talked about, managing unstable chemistries, improving process conformity and yield, it all boils down to the long mean time to replacement. How, these parts needs to be replaced in the chambers, in the tools, wherever, in the fabs, wherever they need to be. How we can increase that how can we increase that mean time for replacement? And all in all, it's all about that improved profitability. Because like I said, when we are spending billions of dollars on a fab, and we're spending, so much time and effort to perfect the process, and we're spending, our energies to make sure that we are providing the best technology to our customers, it has to mean something to the bottom line. And the bottom line is the improved profitability. And that is the most important thing, that it all comes together and it leads to, the success. And like I said, this is not only for us, it's not only for fabs or tool makers, this is everybody throughout the supply chain, that these are the things that they are looking at. How we can improve the process conformity and yield. What can we do to manage the unstable chemistry? And all in all, long mean time to replacement. So I want to, close this topic here, and I'll switch gears a little bit in a little bit slightly different topic, but I want to make sure that it's connected, because again, keep in mind, improved profitability means also that you have to stay ahead of the market. So what we're looking at is some of the innovation in valve technology, what has happened over time, and what, if you're not staying ahead of the market, we are going to be left behind, because the market needs are constantly evolving. And everybody on the call is related to semi. We know how fast the market needs change. We understand how all of those things that we have been discussing over time continue to evolve. And we understand that if we don't stay ahead of the market, we're going to be left behind. So what I did was I just put together a few things in here that the market has done, and what we can learn from. So just as simple, I'm going to start very simple, looking at the ultra high purity springless diaphragm valves, and some of those things where we went from single piston to double pistons, looking at the conventional on the left hand side to the a more innovative valve on the right hand side. Um, um, and what's changed? The conventional, the valve had a seat designed for optimal shutoff performance, in a different angles, different thermal expansion, different media, different material. And then when we are innovating, we're looking at all those factors. When we're looking at the chemical attacks, we're looking at the thermal variations, we're looking at the the swelling and all those factors. The teams are working on trying to make sure we pick the best material for the application. So we have to continue to improve our the seed design, the seeds, all the valve aspects. So I just picked a couple of the simple ones to show. If you look at the innovation in the button design, the button design improved in innovative on the right hand side. If you look at the button design, the way it's designed, it's better alignment control with seat. So on the left hand side there's a button, and it goes on the diaphragm. But then how do you control it, what you do, and all those things. You look at the newer design, the innovative designs that we're looking at. It essentially eliminates the off-center loading from the actuator, which improves the sealability, which improves the forward and reverse direction, all those things. So all of these things, that the aspects that we're looking at, they continue to improve the valve and the needs of the market. And one of the things that we continue to hear about is higher flow. We continue to hear about, we need more flow, we need more flow. So what we had done was we came out with this ultra high purity, high flow, and high temperature valve. We talked about it, total thermal immersibility, looking at all the factors that are on here. We talked about, looking at ultra high purity. So, the RA finishes and all those things that are required, the flow rate, the industry is trying to get more material or more media onto the wafers as quickly as possible. So coming up with the flow rates of 1.2 CV or 1.7 CV was critical. So again, continue to innovate, continue to make sure that we understand the needs of the market and continue to offer the solutions. Ultra high cycle life, the bellows valves are sometimes not considered ultra high cycle life, but these are all the things that are being considered by us and other manufacturers for that matter, to make sure that we are continually offering the solutions to the marketplace. And that's what our goal is, to stay in ahead of the market, continue to stay ahead of the market, continue to offer the solutions that are needed for the marketplace, and then improve everybody's profitability and in the process. And then last thing I would leave you, this is my penultimate slide, is it just also the use of computer-aided engineering. I mentioned it in a little bit earlier, but it's extremely important that we have, we utilize these tools. We at SwageLock, we utilize these tools a lot, and I think as our customers and our suppliers, they look at their systems, they are tremendous tools, for stress calculations, for the CFD, the computational fluid dynamics, the pressure drops, and all those things, and the flow modeling, the purgeability that we talked about. We talked about purgeability a lot. A lot of these packages can allow you to model those before you even cut the metal for the first time, or cut the plastic for the first time, whatever part you're making. But all of these things will only support the innovation that we are going with. So all in all, in summary, I just wanted to, leave you guys with, what are some of the things that we discussed today? We understanding the typical advanced wafer process challenges. We talked about handling the unstable chemistry. Talked about the maximizing the production yields, how to manage some of those issues. Recognizing the ALD process challenges, we looked at some of those things, which are pretty intertwined with general industry challenges that we see. And then last but not least, that we looked at some of the innovation technologies that are extremely important to make sure that we stay ahead of the game, so that our customers' demands are being met. And all of these things basically culminate to reducing the total cost of ownership and improving the profitability. With that, I am going to hand it over to my good friend, Mr. John Butler.
Well, thank you, Masur. We have reached the question and answer portion of our webcast. Once again, you can enter any questions you have by hitting the Q&A tab at the top of your screen, and typing them in. Just to get things rolling, we've got some frequently asked questions that we'll address until we get questions and answers in that box. First question: how important are the materials of construction for valves in ALD production processes?
Good question, John. Thank you. The one of the things that I talked about earlier, and I'm not going to try to move back to that slide because it's going to give people seizure. I'm going to go really fast there, but it's extremely important. You have to understand the media really well on what is going to go through that valve or fittings or any other component that you're looking at, and that media has to be very compatible with the material of construction that you're picking. So if you're picking a valve that is going to see extreme chemistries, you may have to look at things like Hastelloy or things that different than your traditional stainless steel that we look at. Some of those things become very, very critical. So when you're looking at those valves, when you're looking at those media, I'll give you a quick example. The DRP, the Teflon valve that we use in CMP applications, it sees hydrofluoric acid. So the hydrofluoric acid eats through the stainless steel and other, even Hastelloy and other metals. So we have switched to Teflon because Teflon was one of those things that withstands the hydrofluoric acid. So you have to really understand your media and try to make sure that we're picking the right material of construction for that.
Okay, well, thank you for that. Here's another question. What other fluid system related factors should be considered that impact chip production yields?
Repeat that question again, John. Sorry.
What other fluid system related factors should be considered that impact chip production yields?
Good question. Thank you. So some of those things, I would say, obviously I highlighted only a couple of things here, but there's several factors, and obviously, we have technical people on the call. They understand this, but your lines to a valve, in a system, when you're looking at the system related, you have to look at in and out on the system side of things, not only looking at the valves or tubing or fittings or that, but you have to look at on the system level. So when you're looking at the fluid system as a whole, you need to be able to understand how the flows are, where the pressure drops are, where your lines are coming into the valve and how they are responding. The actuators are responding times, the CDA, the clean dry air, how is that being provided, what kind of lines that is. And so there's a whole slew of factors that goes into the design of the whole system, but it has to be system thinking. It cannot be just a valve thinking, but it has to be system thinking. And then you focus on the valves that are going to perform the best in that system.
Okay, all right, thank you. Here is another one. What is the benefit of having the ability to increase flow to the process chamber?
Good question. So, I know there were some of the attendees that I was looking at earlier are the gas producers and gas suppliers. One of the big advantages, you can process faster, right? So if you can only get so much media into the chamber, you can only process so much. So when I talked about the wafers are getting from 150 to 200 to 300 millimeters, there's the need for getting more and more gas into the chambers to have those processes and reactions quicker is increasing. That's one factor. And the other factor is the lines are getting smaller and smaller. So you want to be able to have the reaction and get it in and out very quickly. So you bring a lot of gas and you exit or purge a lot of gas very quickly. So those are the two factors that are driving, continually to add more and more gas into the chamber.
Okay, all right. Here is another question about purging. What factors drive the purging of gases from the system?
So factors, let me understand the question really well. So the factors, I know we talked about the purging and how important the purging is. But like I said, one of the factors that, when we look at a lot on the reaction gases. When the gases are coming in, we focus a lot onto those gases. And we figure out, okay, we're going to bring this gas, and it is going to have this reaction. And then, it's going to exit, and then we're going to bring next gas, and so on and so forth, continually. So the factor that's driving the purging is how fast can you get it out so that the next gas can come in? Because unless there's a continuous flow of those gases from in and out, it's very difficult to try to figure out that, I'm going to bring the next gas, and then if my previous gas is out of the system or not. So purging factors has to be very calculated with the size of the valves, like I talked about in our the size of the valves, the size of the lines, the speed, all those things, because as important as it is to bring the gases for reaction in the chamber, it's equally, or if not more important, to get the reactant gases out as quickly as possible from the chamber to have that fast process. Again, we're trying to maximize the investments in billions of dollars of investment, and how fast can we get the process completed is the name of the game.
Okay. Well, we have about 14 minutes left in this session. So if you do have questions, please don't hesitate to add them to the Q&A tab. Here's a question about total cost of ownership. You talked about valve diaphragm being designed below the fatigue limit and allow for ultra high cycle life. Why then would a valve ever fail?
Oh, great. Wow, that's a good question. That's great. Yeah, this is phenomenal. That when you design a valve below the fatigue limit, then it should last forever, and you will never have to replace that valve. So um, excellent question. So one of the things that typically in the traditional valves, what you see is the failure mode is the diaphragm crack, or diaphragm fails basically after the end of cycle life. When you look at the ALD valves and some of the things that I was talking about, we're designing these below the fatigue limit, so they theoretically they can continue to go for unlimited amount of life. So obviously that is one thing that we look at. So the typical valve failure in ALD technology or DE or a lot of other valves that we see is not a diaphragm failure, but there's so many moving parts in the valves, in the actuator, O-rings, and the lubes and all these things. So a lot of time it's not the diaphragm that fails. So you have that fatigue limit and you have that defined, but a lot of time we're seeing that the actuator has lived its life. So the limiting factor sometimes becomes the actuator design, or actuator, the O-rings and things like that that are in there. So again, looking at that technology and trying to figure out how we can predict that. Can we look at the actuator performance and be able to figure out that it's time to replace it, or it's time. So your diaphragm might not fail, but then there's a lot of other moving parts in that valve that end up failing, or not performing as to that unlimited cycle life. So yeah, we'll be out of business also if we have unlimited cycle life, I think. So that's something that we continue to propagate. That so kidding aside, I think we obviously we design it to the maximum cycle life, but obviously there's a lot of moving parts beside even diaphragm. So diaphragm is the one that's designed for unlimited cycle below the fatigue limit, but there are a lot of moving parts that they end up failing.
Okay. Well, I don't see any additional questions in the chat. Oh, wait, I'm sorry. Here's a later arriver. Are high-speed, high CV valves also needed on the exhaust side of an ALD process chamber?
Depending on your design, yes, because again, keep in mind that sometimes it's the exhaust that is the limiting factor for your system design. So you have to look at the whole system and how you're exhausting that chamber, or where you're exhausting that chamber. So sometimes, I tell you, some of our customers do use our ALD 20, which is the high flow valve at the exhaust side, because that is what limits the process speed. So absolutely, yes.
Okay, great. Okay, here's another one. Um, have you seen a need in the market for a rebuildable version of the ALD valve? If so, has that possibility been explored?
Good question. Yeah, good question. Now, so we hear, obviously, we hear about the rebuildability of the ALD valves, and we hear from our customers, because they want to be able to open this ALD valve and, able to clean the diaphragm, or, replace this or replace that. Um, so we do hear about those things, and I think there's something that obviously we are able to address. But all in all, what we talk about, and what is critical and important to understand, in this design discussion that we're having, is how important that flow rate, how important is the criticality of the cleanliness, the criticality of, going back to that original valves and all those things. So it's extremely critical, all, with all those factors that I'm discussing, is it's, the rebuildability is just not simple as, hey, let's take the valve and just, put a new this and new that in there, and then, so it has to be considered very deeply and very thoroughly to be able to offer that solution to our customers, because we're, any valve maker want to make sure that they are putting their name on rebuildable valve also, as well as the new or rebuild valve, as much as on the new valve that we are. So absolutely, we hear about it from our customers. We have dabbled into investigating it, and some of those things. It's just at this time we are not offering it.
Okay, all right. I believe that is all of our questions. So if you would please advance to the next slide, we will wrap up. If you are interested in learning more, you can contact us via the Swagelok Sales and Service Center locator form. Upon submitting that form, a representative from your authorized Swagelok Sales and Service Center will reach out to you within 3 days. If you're interested in learning more about this topic, you can go to our blog on Swagelok reference point entitled How to Solve Top ALD and ALE Semiconductor Process Challenges. And then finally, an on-demand version of this webinar will be available to you via that registration link, which will take you to swagelok.com. And Amber will be putting that link into the chat of this meeting. Please always stay up to date with us by following Swagelok on various social media channels, including LinkedIn, Facebook, Twitter, and YouTube. So with that, I will thank you very much for your time and attendance. We hope that you found this session to be helpful and informative, and we will wish you to have a great rest of your day. And thanks for joining us.
Thank you, everybody. Really appreciate your good questions and your engagement. So thank you so much.